Good morning, friends. In previous lecture, we derived equation for the analysis of fin, and in that equation, we find two constant C1 and C2 in second order differential equation, and we already know the solution of that second order differential equations, and to find that we have to consider a three case for the fin. In this lecture we will study about different cases and solution of Finn's equation for particular cases. So this equation we derived in our previous lecture. Theta square d square theta upon dx square minus m square theta is equal to 0, and this is the solution for that second order differential equation, in which we have to find C1 and C2 to solve that equation. So for that we are considering three cases. So this is the first case in which the fin has infinite long. So at the end of the fin the temperature is approach to T infinity. As we know that we use T infinity for atmospheric temperature. So as the length of fin is too long, the end temperature is remain at atmospheric temperature. So for analysis the end temperature we consider T infinity. In a general case, if we have 800 mm long fin or rod, so this case is applicable for that. So here in left hand side we are starting at left hand side is x at x is equal to 0, and right hand side end is x is equal to L, approximately infinity, and this is the temperature profile for that. We are applying heat at the left side, so the temperature of left side is T0, and gradually it is decreasing to the atmospheric temperature at length L. For this case the boundary conditions are at x is equal to 0 temperature is T0, and as x is equal to L temperature is T infinity, and we also know that theta is temperature difference. So for at x is equal to 0 theta is equal to T0 minus T infinity, so the difference is theta 0. And for end we having T is equal to T infinity, so theta is equal to T infinity minus T infinity is equal to 0. Also we have second order differential equation solution, that theta is equal to C1 e raised to mx plus C2 e raised to minus mx, and applying this both boundary condition in this equation, so we are putting x is equal to 0 and T is equal to T0, so we get this term become 1 as we are putting x is equal to 0. So our equation will be theta 0 is equal to C1 plus C2. Now next, applying boundary condition second, that x is equal to L and t is equal to t infinitive and theta is equal to 0. As we put x is equal to infinitive, we get c1 theta is equal to 0 and c1 into infinitive. As we are putting x is equal to f, this term become infinitive and plus this term becomes 0 as it is minus infinitive. So 1 upon infinity is equal to 0. So here this term is infinitive, so here if we put c1 is equal to 0, then we can say that this equation will be satisfied. So the answer of c1 is 0, and we will put this value of c1 in this equation. So we will get c2 is equal to theta 0 is equal to t0 minus t infinitive. Now we have c1, value of c1 and value of c2 put in our previous equation. So we get theta is equal to c1 term becomes 0 and here c2 term is, so we are putting c1 and c2 in this equation. So theta is equal to 0 plus t0 minus t infinitive e raised to minus mx. Differentiating this equation, we get d theta upon dx is equal to t0 minus t infinity as it is constant, and e raised to minus differentiation of e raised to minus mx is minus m e raised to mx. So here we have minus m e raised to minus mx. Rewriting this equation, so we get t minus t infinitive is equal to t0 minus t infinitive, and t minus t infinitive putting in this in left hand side, so we get t minus t infinitive upon t0 minus t infinity is equal to e raised to minus mx. So this is the temperature distribution for infinite long fin, and here if we want to find the temperature at particular distance, we know the atmospheric temperature for that system. Now if we know the input temperature and m is the constant, it is pH upon Ka, these all are constant parameters. So applying this length x, we can get the temperature for particular distance. So this is the case 1, and in which we also find the heat conduction Q is equal to, we know the equation of Q is minus Ka dt upon dx. For that we are putting d theta upon dx at x is equal to 0 as we are considering base. And we also derived this equation d theta upon dx is equation number 6. D theta upon dx is equal to minus t0 minus t infinity m e raised to minus mx. So putting this, and at base x is equal to 0, so it is minus Ka minus t0 minus t infinity into m, and we all know that m is equal to p into h upon Ka. So rearranging this equation, we get Ka hp t0 minus t infinity. It is the heat transfer by conduction at base. Now we all know that we considered an element at which the heat transfer is occurred due to conduction and also due to convection. So the heat transfer by convection Q is equal to 0 to infinity. This is the length of our pin. We know the equation, it is HA delta T, and HA, A is equal to perimeter into thickness. So P into dx T minus T infinity. And from equation number 7, from this equation we are putting the value of HP T0 minus T infinity e raised to mx in mx dx. So we don't know the value of t as we don't know the distance. So we are just replacing t with t0. So from this equation we can get t minus t infinity is equal to e raised to minus mx t0 minus t infinity. And integrating this equation we get minus 1 upon m e raised to minus mx from 0 to infinity, and applying these limits, so we get minus mx e raised to minus m infinity minus e raised to minus m 0. So this term become 1 and this term become 0 as it is minus infinity. So we get hat 0 t infinity minus 1 upon m. So rearranging this equation we get this equation and put the value of m. M is the root of hp ka. So rearranging this equation we get root of ka hp t0 minus t infinity. So at the x is equal to 0, the heat transfer by the conduction and convection are same in long fin. Thank you.